Hi, I'm Pranav, and today I'll be presenting a group project titled Automated Weed and Crop Detection Using Deep Learning. Let's come to our motivation. Let's start with the motivation behind this project. Modern agriculture is facing a major challenge, which is the need to increase food production sustainably. This is complicated by environmental concerns, labor shortages, and rising costs. Farmers are under immense pressure to produce more with fewer resources and minimal environmental impact. One major issue is weed identification and management. Traditionally, this process is done manually or with generalized herbicide application. However, manual identification is time consuming, error prone, and costly, especially on large farms. Mistakes in this process can lead to underperformance in crop yield or excessive use of herbicides, which damage the environment. Let's come to a problem statement. The central challenge was building a model that works robustly in real world conditions out in the fields where there is a variation in lighting, plant growth stage, and etc. Our task is to develop a multi-class classification model that can take an image of a seedling and classify it into one of the 12 plant species, which include both crops and weeds. Let's come to our input and output pipeline. The inputs to our system are these raw plant seedling images. The images are pre-processed and then passed through a model, which then predicts the class by assigning a probability score to each of the 12 categories. The output, we visualize the image along with the actual and predicted labels, helping us visually verify performance and understand misclassifications. Let's come to our methodology. The first part is the data pre-processing and augmentation. To help our model generalize well, we applied data augmentation using TensorFlow's Keras API. This included random flip, both horizontal and vertical, and random rotation, minor angular shifts. This way, our model could learn to handle real-world variability like different camera angles or plant orientations. We also resized all the images to a consistent input shape and rescaled the pixel values to fall within a range to stabilize training. Now, and the second part, what we did was class imbalancing. Some plant species had hundreds of samples while others had far fewer. This imbalance could bias the model toward the dominant classes. To correct this, we computed class weights using compute class weight from scikit-learn. These weights were then passed into the training process so that underrepresented classes received higher importance during backpropagation. The model architecture consists of a CNN. We used CNN as our primary model. And within our CNN consisted of multiple convolutional 2D layers with ReLU activations to capture both low-level edges and complex textures. A dense layer with 128 neurons and ReLU activation to integrate spatial features. And a final dense layer with 12 softmax neurons to output class probabilities. For the training configuration, we used loss function. The loss function we used was sparse categorical cross entropy, which works well with integer labeled datasets. Optimizer, we used Adam Optimizer for efficient adaptive learning, and for logging, we used TensorBoard. We trained the model for 5 epochs, which was sufficient to reach convergence without overfitting. Optimization strategy which we used was layer-wise feature extraction, and by this, what I mean is we stacked filters, then we allow the model to progressively learn intricate patterns. For the activation functions, we use ReLU throughout to maintain gradient flow, and dimensionality reduction, we used pooling layers, help reduce overfitting and computational cost. Now, coming on to the baseline model comparison, before building the final model, we experimented with a simple baseline CNN, which used fewer layers and no class balancing. Our results, the baseline training accuracy was at 80%, and our baseline validation accuracy was at 76%. Clearly, the model struggled with generalization and showed signs of overfitting. This confirmed that deeper architecture, data augmentation, and class balancing were necessary. Coming on to our final model performance. Now here's how the final model performed. Our best training accuracy that we got was 88.61%. The best validation accuracy that we got was 86.99%. These close values indicate minimal overfitting and strong generalization. The model was also evaluated using a classification report, which showed balanced precision, recall, and F1 scores across all 12 classes, meaning it didn't overly favor any one category. Now coming on to a visual result, let's see an image related to our predictions. This, in most cases, the model was accurate. In edge cases where weeds closely resemble crops, the model still maintained above 80% accuracy. These visualizations helped us identify which categories still need improvement, like classes with fewer training examples. Now, coming on to our team and experience, our team consisted of Gaurav, myself, Pranav, and Vikalp. I had some previous experience with OCT scans, and other teammates had none. Despite the varying experience level, we collaborated well, shared knowledge, and supported each other. That'll be all for our group project. Thank you.